All right, I am back from the break, and we were looking at, before we left for the break, we were looking at units conversions. Now the units conversions are important skills, so these are worth playing around with a bit. One of my favorite examples with units conversion is this. Let's say that we have a car, and it's going 10 meters per second. Now why am I interested in a car going 10 meters per second? Because not so much this chapter, but the rest of the course. You know, I started out saying chapter 1 is not really very representative of the kind of problems that we're going to run into. It's very unlikely that you would have a problem just in units conversion show up on a midterm. But it's very likely that there's another problem that's going to show up on the midterm where you may have to do units conversion. So again, chapter 1 has some of these tools in them, and the good news is, if it's not entirely clear what we were supposed to learn from chapter 1, you'll find out in the future chapters. So you'll see it, it'll come along, it's going to work out fine. But in any case, what's going to happen in future chapters, in chapters 2 and 3, we're going to start looking at motion, including velocities, acceleration. So if I have an object, like a car, cars are easy examples to set up in a problem. Maybe it's going 10 meters per second, or maybe it's going 20 or 30 or 40, and I'm just not familiar enough. Meters per second is kind of a new set of units for me, and that's because maybe I'm used to miles per hour. And so the time units are different, the distance units are different, but working in meters per second actually is pretty handy. I mean, I would totally be in favor of, well, maybe not, I'm not sure, I guess. I wanted to say that I would be in favor of having all of our speedometers on our cars be in meters per second instead of kilometers per hour. Let's see, so 10 meters per second, what would that be in miles per hour? Because what I want to do is when I read that homework problem, I don't want to have to stop and think about how fast that is. I already want to have an idea of how fast that is. So let me do this. I'm going to take a mile, and I'm going to put in the 5,280 feet, because that's how many feet there are, and turn that into inches, and take the inches and turn them into centimeters, and take the centimeters and turn them into meters. It turns out that all of these conversions are exact. So if I have something that starts out as exactly 1 mile is exactly 1,609.344 meters. That is an exact conversion by definition. That's how that works. Now, I'm going to round that a bit. I'm going to round it to 1,600 meters. So if you think of, like, you know, track events, you know, the Olympics are coming up sometime, no matter, the Olympics are always coming up sometime in the future. If you think in terms of like the Olympics and watching the track events, if we're running track with British units, that's like 4 times around the track is a mile, right? So 4 times around the track would be, and what is it? It's 440 yards each time around. Well, 4 times around would be a little more than 1,600 meters. So internationally, when you're out doing the track events, it's 400 meters. So 4 times around at 400 meters gives us 1,600 meters, which is very close to a mile. Anyway, just trying to try to get some examples so that these become very familiar for you. So let's do this. Let's say now the velocity then of 10 meters per second. I can take out the meters. I'm going to say 16.09 meters is 1 mile. That's enough precision with 4 significant figures. And then how many seconds are there in an hour? And that would be 60 times 60. So that's 3,600 seconds. So that conversion says that 10 meters per second is 22.369. It's going to be like 22. I don't think I have enough. I should have put 16.09344. Anyway, I'm just going to round these. I'm going to say that 10 meters per second is about 22 miles per hour. 20 meters per second, if I double that, is going to be about 45, 30 meters per second is about 67, and 40 meters per second is about 90 miles an hour. So you can think of it this way, 10 meters per second, that's how you're supposed to drive, like in a school zone where you're slowing down watching for the kids. And 20 meters per second, that's 45 miles an hour. That's, you're driving out on kind of an expressway or something. 67 miles an hour, that's kind of like freeway speeds posted, and then and that would be 30 meters per second. So here we are driving in a school zone. Here we are out on maybe a faster moving highway. Here we are out on the freeway, at least the posted speed, and then this is how fast people actually travel on the freeway. It's more like 40 meters per second, right? Or if it's a baseball pitch, right? If if in baseball, if they're pitching, maybe it's a 40 meter per second pitch. Okay. Anyway, think in terms of your favorite examples of what is 10 meters per second. Think of something that's 20. Think of something that's 30, something that's 40. And then when you read these homework problems, and it says the car's traveling at 25 meters per second, you go, yeah, I know how fast that is. Okay, so it makes it more real for you when you're looking at these examples. Now we have kind of the later part of the chapter is looking at order of magnitude. So I want to say this. I want to say, again, I know I've said this a couple times already, but this chapter is not representative of the sorts of problems that you're actually going to see in homework, but there are some important tools here. And I'm going to say the most important tools are, first of all, understanding units. Okay, so that's the first thing you want to be really clear about. You want to be able to do units conversions. So units and units conversions, know what a meter is, or have an idea of what a meter is, a second, a kilogram. Be familiar with scientific notation. Be able to carry out calculations using scientific notation. A lot of times students do really, really well in all their math classes, and often that's, well, I feel like often that's because they have not been asked to keep track of units, and a lot of things, you're never asked to actually carry out calculations of a bunch of numbers in decimal form. So this is your chance to do that. And it's kind of fun. All through high school, I enjoyed math. I liked math. I still like math a lot. So math I really, really enjoy. But it wasn't until my freshman year in college when I first took physics. I was a chemistry major to start out with. And I took physics because that was required if you were a chemistry major. And physics was fun. Physics was fun because all these real life situations, and you got to do calculations. You got to pick out different formulas that would apply and identify what quantities were related to what. You could put numbers in, keep track of all the units, and you could imagine all these things happening. So this was kind of mathematics brought to life. I hope that works. I hope that in the course that you're able to build an intuition about these things and kind of enjoy kind of the fun of figuring out how things operate and being able to carry out meaningful calculations. All right, we're going to, so I guess on my list, I got kind of, make sure that you're good on units, make sure that you're good at units conversion, scientific notation you should be familiar with, make sure that you have an idea of what uncertainties in measurements mean, and again, those are mostly going to show up in lab, and then be able to calculate the percent uncertainties or relative uncertainties. Those are the important things. And again, you're going to have plenty of chances to do that. Okay, so take advantage of those. Now, the later part of the chapter is looking at doing estimates. Now, estimates can be useful. So I am going to go through a few of these examples, but I'm also going to say carrying out these estimates, if you can kind of get the feel for them, that's great, but they're not as essential starting out right now. So here is this beautiful mountain lake up in maybe up in the Sierra somewhere. Ooh, looks like it's time to get out backpacking. That's really pretty. And so, you know, you're out backpacking and you come up to this lake and you go, I wonder how much water there is in this really, really pretty lake. And so you look out at it and you go, what shape is the lake? Okay, it's circular across the surface. Now, of course, it's not circular, but it's not a bad estimate. So the idea is, can we say something meaningful about how much water is in the lake? And, you know, there's a good chance we can, that we can actually say something that has some meaning to it. And so what this person who's been out backpacking determines is they go, you know, looking across, I'll bet that's a kilometer across. Now, that's going to be a bit of an estimate, right? And so that could be off by 10 or 20, 30%. But they're saying, yeah, it's about a kilometer across, and how deep is it? Now, this one's really suspect, right? So, you know, you go out and you swim around in that lake for a while, and you go, in places I can see the bottom, but at the center part, and you know, if you're backpacking in the Sierra, you know that you can see through these lakes to a pretty good depth. The center, you're going, wow, it's really deep here. So, you know, you end up guessing that it's 10 meters. So that's a way to estimate how much volume there is. So let's see what that calculation might look like. So again, this is not going to show up on the midterm, I don't think. It's not. It's not going to show up on the midterm. So here was that lake, and so what you can do is you can go, well, the volume is, for a cylinder, it's kind of cylindrical in shape, is what we've determined, is pi, r squared, times h. Now, you don't have a calculator handy, or maybe you do, I don't know. Pi can be rounded to just 3, right? A factor of pi is like 3, pretty much, if we're just getting an estimate. So what they're doing here is, what I'm doing here is just getting an estimate. Okay, maybe the radius is 500, the height is 10, pi is equal to 3. So I'm going to say 3 times 500 squared times 10. The volume, can we do this without a calculator? I think you can. Let's see, factor of 3, 5 squared would be 25, and 3 times 25 is 75. Now that gives me a number of 75, and then how many powers of 10 do I have? I've got 1 power of 10 here. It's not a coincidence that the person just imagined the depth to be 10 meters. That's something that calculationally is easy to deal with. That's 10 here. And then we've got 4 zeros here because there's 2 and it's squared. So I got 5 zeros and a factor of 75. That puts me at 7.5 million cubic meters. This was all done in meters. So show me a cubic meter. What does a cubic meter look like? Cubic meter looks like this, by this, by this. Every physics student carries a cubic meter measuring device with them everywhere they go. That's my cubic meter. So I got 7.5 million of those, and that's the volume estimate. Hey, anybody have an idea of how many kilograms of water this might be? How many kilograms are there in a cubic meter of water? So let's see, there was that liter we talked about. We said that 1 liter of water would have a mass of a kilogram. How many liters are there in a cubic meter? So a liter is 1,000 cubic centimeters. So a liter would be 10 centimeters by 10 centimeters by 10 centimeters. That would be a much smaller cube. 10 by 10 by 10 would be a liter, and that would be a kilogram. Well, how many liters would fit in a cubic meter? And a cubic meter, since a liter is 10 by 10 by 10 centimeters, I could line up 10 of those liters along each of the directions in my cubic meter. That would give me 10 by 10 by, that would give me 1,000. There are 1,000 liters in a cubic meter. Cubic meters are big. So a liter is a kilogram, a liter of water, sorry. specifically, it's based on the density of water here. So a liter of water would have a mass of a kilogram. If I have 1,000 of those liters, that would be 1,000 kilograms. That would be a ton. That is a metric ton. 1 cubic meter of water is a metric ton. I'm guessing you can't lift a cubic meter of water. It's a lot, okay, of mass. So that would be 7.5 billion kilograms of water. And maybe mass is a good way to represent that. Okay, kind of fun, I guess, I hope. Let's see, let's measure. Another example that they suggest here is, how would we get the thickness of a page? How would you estimate the thickness of a page of the textbook? And they give us a hint. They say we don't need this caliper measuring device. So, here's the textbook. I can't hold this up enough times, right? So there it is, Physics for Science and Engineers. My kids, when they were little, you know, when they were growing up, they'd see all my books around and they go, "How come all your books have the same name, Dad? They're all Physics for Scientists and Engineers," and they were right. Anyway, let's see, how are we going to measure the thickness of one page? And so I took this very textbook, this very one, and I ignored the cover flaps, and I got out a ruler, and I measured the distance of just the pages to be 4.1 centimeters. And so I took the number of pages, I counted the number of pages. Now the number of pages was 1,228, but I realized the numbering, they number both sides of the page. So there's actually, for 1,228 pages in the book, there's really only 614 sheets of paper. So that is, right there, that's 614 sheets of paper, roughly. I don't know if I got all the counting on the appendices completely correct. So that would be at 614. So what I can do is I can take that 4.1 centimeters that I just measured with a ruler that I just had lying around, 4.1 centimeters divided by 614, that came in at 0.0067 centimeters. Now, I could put this in millimeters, but it's still less than 1/10 of a millimeter. So I put it in microns. So I said 10 to the 4th microns is 1 centimeter. Now, I could have written this as 10 to the 6th microns is the same thing as 100 centimeters. Anyway, it worked out to be 67 microns. Okay, so, or did it? Okay, now I'm worried. I'm a little sus. No, I think that works out, because moving the decimal to here would put it in millimeters. Microns would be a factor of 1,000, so the decimal would move to here. So yeah, 67 microns is the thickness of the page. Now, I can take that number and I can just invert it. So this is a trick that shows up in different sorts of calculations. Instead of saying it's 67 microns per page or per sheet of paper, I can take that one sheet of paper and divide it through by 0.0067 centimeters. When I do that, my calculator tells me that's 150 pages per centimeter. So it's 15 pages per millimeter. So, cool, right? If I count 15 of these sheets of paper and press them together, I'm guessing that's going to be pretty close to a millimeter. It would not be a very accurate measurement, just looking at 15 of those, but by looking at a large number, by looking at 600 of these pages right next to each other, I'm going to get a much better measurement of how much thickness they have. Now, here's another one of the examples that they came up with. I'm not too sure about this one, but let's take a look at it, I guess. It says that you've got a building over here. Here is my building. It's 1, 2, 3, 4, 5 floors on the building. And it says that, you're at the bus stop waiting for the bus, and you look over and you go, look at that building, the apartment building over there. I wonder how tall it is. So I wonder if there's a way I could estimate how tall that apartment building is. Now the person here apparently knows their own height, and they are able to estimate the elevation where their eyes are. Okay, so this takes a little bit of doing here, but the person estimates, oh yeah, up to my eyes, everybody knows that measurement, right? 1.5 meters up to where my eyes are located, and then the person estimates stepping away from the bus post, the bus sign, the post that's holding the bus sign. I think that's a bus sign, right? Yeah, it says a bus stop pole. So here's the bus stop pole right there. And so the person, again, somehow knows that that is 3 meters high. I think they had to have a tape measure with them to do this reliably. Because, you know, if you're standing here looking at the bus, I guess you could estimate it. They estimate this at 3 meters, and then they step back 2 centimeters, they step back until their sight, their line of sight, goes right over the top of that pole, and it lines up with the top of the building. So that's what they're going for. They're going for, is there some object not so tall right next to me that I can measure, and then I can stand back, and when it lines right up, I'm going to be able to measure the height of my eyes, measure the height of the pole, and measure how far back I was. Now maybe they did have a tape measure with them. I don't know. Maybe they had a tape measure with them and were able to make these measurements, or maybe they just estimated them. But what it turned into was a diagram. And it's a diagram using similar triangles. I hope that's a concept that you enjoyed in your math classes, because similar triangles are great. We can use those in diagrams all the time. And we are going to be using diagrams all the time. I should point that out too. Diagrams are just really, really useful to have. And so we're going to be using diagrams all the time. More often than not, when we have an example come up, first thing we do is draw a diagram and try and visualize what's going on, what's happening in terms of that diagram. All right, so what the person determined then is that oh, they still had to do the 16-meter measurement too, right? So here's the diagram they set up. What they identified was that if we use the person's eye level as a baseline, they had to measure 2 meters out to the bus stop pole and an additional 16 meters out to the building. So they did walk over to the building and make a measurement there. And I guess that's it. And then, the top of the bus pole is 1.5 meters above eye level. Okay, so I drew the diagram. So here's the diagram here. And what I did was I said, here is the height of the building. So it's always good to remember what it is you're measuring. Sometimes you can lose track of that. So I go, okay, H is what I'm after. Now, I can use similar triangles. What I can say is that X, this distance right here, is to 1.5 as 18 is to 2. So the similar triangles here are this little triangle right there. That's one of them. And then this big triangle. Now you guys know similar triangles have the same set of angles to them, but they could be scaled, so you know one of them's bigger than the other. So this right triangle here, it's a right triangle, so it has a 90-degree angle. The angles here and here match the angles here and here. And so they're similar, and that means we can use ratios between the sides. So X, from this set of numbers here, X works out to be 13.5. Now X was measured with a baseline of the person's eye level, and so we have to add on the additional 1.5. Anyway, we ended up with 15 meters. Now, is that a sensible answer? And I wasn't so sure about this. If we go back, how many stories are in the building? And it looks like we have 5 stories. 1, 2, 3, 4, 5. if the building is 15 meters high, then each floor is just 3 meters. And 3 meters would be 9 or 10 feet. I guess that's enough. If you have ceiling heights of 8 feet, which is common, and then a couple of feet for the structure, you know, one person's floor is another person's ceiling. Yeah, that might work. 15 meters might be a reasonable height for a 5-story building. Okay. All right, this one's a little over the top, maybe. You guys decide. And again, I would say, you know, don't worry about these this example for sure, and these other examples that we're taking a look at. We're just, you know, setting up some diagrams and seeing, you know, developing some problem-solving skills. So this is kind of interesting in that if you get to the shore of a large enough lake and you look out across the lake, you can actually measure the curvature of the Earth. So if you look out far enough, you realize that there's a horizon beyond which you just don't see any of the surface anymore. So what they're saying here is that this person climbs up on this ladder, looks out over this pretty good-sized lake, and it seems to be that there is a definite horizon. They're claiming it's at the other side of the lake. I'm not sure how they made that that determination. Let's see. Yeah, they're saying that the, you know, objects on the opposite shore appear to be right out at the person's horizon from this, and there's not much you can see beyond that. In any case, what they're estimating here is that the ladder is 3 meters high. You can just see rocks at water level on the opposite shore. So you get out a map, and the map tells you that the distance to the other shore, from the map, it looks like the water's about a distance of 6 kilometers, 6.1 kilometers. So is this going to work? I guess yeah, there's a step ladder and the height of the person combined says that eye level is going to be at 3 meters. Now, I think you can already see that, you know, you could draw a diagram here. What we're going to do is we're going to draw, here's Earth. We're going to draw that as a sphere, and then there's going to be a radius out to the far end of the shore, and then a radius here. Now, you might be looking at this and going, well, that diagram isn't to scale. The Earth, you know, has a circumference of 40,000 kilometers, not 40. And so, but if we actually do it to scale, we really wouldn't be able to see what's going on. So we have altered this a lot, so that we can use the diagram and possibly write down some information. So the idea here is this is a right triangle. We're going to assume that what we have set up here in the diagram can be, you know, reliably represented by a right triangle. The height here is 3 meters right there. So what we're going to do is take the radius of the Earth, of planet Earth, and add on 3 meters here, and then put in the distance. So the distance here is going to be 6,100 meters. So using Pythagorean's theorem, we could say that the side here is a distance r, the side here is a distance d, roughly, and so r squared plus d squared is equal to r plus h squared. Now, when we multiply that out, the r squareds cancel, and we can come in and say 2hr is equal to d squared minus h squared. Now, h squared is so tiny compared with d squared, we're going to ignore h squared in this calculation. So that leaves us with the radius of the Earth we're estimating to be d squared over 2h. And putting numbers in for those gives us a radius of the Earth of 6.2 million meters. Now, kind of the accepted value for and the Earth's not a perfect sphere, but the radius of the Earth is measured to be about 6.37. So they came up with 6.2, which is actually, that's pretty good if you can stand on a stepladder and look out over a lake and estimate the radius of the planet Earth reliably. But that's what they're claiming they've done in this example. Anyway, again, it's just, getting to think about what measurements mean, how measurements are carried out. So when we're working with different physical quantities, we said that they're going to be combinations of different units. So for example, dimensions of speed or velocity. When we write down the velocity or the speed of something, that's going to be in meters per second. And so what that is, I can write that as meters per second, or I can say that it's a length divided by a time. Now, different quantities are going to have different units associated with them. So units are going to become your friends. So units will help guide you through a problem. If you've done a problem and you look at the units and the units don't make sense, then there's no sense in getting your calculator out, because there's still a problem with the way things are set up. So for example, what they're saying is this. Let's say you're working through a homework problem and you're trying to remember what the formula is that relates velocities to accelerations and time. So you see this equation written down, but then you look at it and go, well, that can't be right, because the units don't match up. Units for velocity would need to be meters per second. And units for a starting velocity, which is what that is meters per second. We're going to learn in the next chapter that the units for acceleration need to be meters per second, meters per second squared. And if I put in t squared, that's 2 more units of time. And so what's going to happen is the units of meters per second are not going to be the same as just units of meters. So you can actually look at an equation and go, that's not right. The units don't work out. So units become a very, very important check for us. And again, they will guide you through a problem. And that's one of the things you didn't have in most situations in math classes. They're not putting units in. But in physics, and in chemistry, and in biology, and in engineering, you've got to have units in every one of those calculations. Every one of the numbers that you put down, you've got to have units associated with those numbers. Think of the units as your friends. The units are going to help guide you through a problem. All right, so that takes us through all of Chapter 1, so I think we're going to wrap things up a bit early for today, which is fine. And so at the end of these slides also, there's going to be a summary. I'm not necessarily going to go through the summaries in a lot of detail. There may be times that I point to certain things. Again, I'll point to some things. So don't worry about so much. I know in science classes a lot of times they're very particular. What is the scientific method? And the scientific method is not like step 1, step 2, step 3. The scientific method is like make a bunch of observations, think of how that might be described. Make a bunch more observations, see if the predictions from your hypotheses or theories pan out with those additional. It's just kind of a back and forth between developing theories about how things work and then going back and making observations and making predictions. So kind of cycling around, making those predictions and making more observations. Whatever works, if you come up with a formula as to how things work and it just starts matching all the observations, it's perfect. Now there are important features within science that can help streamline the process. Okay, and at the end of the day, I mean, you can't just make stuff up. And unfortunately, we've got a lot of that going on today, where people decide you just say whatever you want. Science is very restrictive. So science is one of those fields that's really, I hope, should be really, really good at sorting out what people are just making up versus what really has observational evidence to support it. Dimensional analysis, units conversions, you want to be able to do those. Uncertainties is important. Be familiar with the units in the SI system. And order of magnitude estimates. If these are fun to work from, and start practicing just thinking in terms of estimates. When you're doing a problem, if you can start the problem out, if you're doing a homework problem or something on a midterm or whatever, if you can start the problem out by going, the answer probably should be in this range, that's a good way to start things out. So, being able to do order of magnitude estimates can be pretty useful. All right, I will wrap up right there. And so if you guys have questions, definitely stop by. So I hope to see a lot of you in office hours. Stop by and we'll get the questions figured out.